Hey guys, Miss Gosling here. In this video, you are going to learn about the different types of energy. By the end of the video, you will be able to describe different types of energy and to calculate some types of energy. So let's go ahead and get started. There are a bunch of different types of energy, and you are probably familiar with a lot of them from your earlier science classes. I know this is something you learn a lot about in 8th grade science. You also may have covered some of this in your biology and chemistry classes. But I want to go through a few of the most common forms of energy because you're going to see them a lot this year. So our first picture, we see a nuclear power plant. So we can call that nuclear potential energy, and that's going to be the energy that is stored in the nucleus of an atom. Next, we can look at electrical energy, which is going to be the energy stored due to electric charges. We have chemical potential energy, which is stored in organic things. So you get chemical potential energy in your food. Now, next to chemical, we have our gravitational potential energy. And that is going to be the energy that something has because of its position relative to a zero. So it's the energy that I have in something because I'm holding it off the ground, essentially. So it's the energy that it has due to the gravitational field or the gravitational attraction between it and the Earth. Next, we have kinetic energy, which is the energy of motion. So if you are running, you have kinetic energy, which you probably got from converting the chemical energy in the food you eat into that kinetic energy in your muscles. We have the elastic potential, which is the potential energy in an elastic system, so due to stretching something back. So a really nice example that you can see here is that somebody pulling back a rubber band to shoot it at somebody else, or hopefully at a wall, as they probably should not shoot rubber bands at each other. You can also see this in things like the string, like a bowstring. We could talk about potential energy stored in a spring, which is kind of a variation on elastic potential energy, not really the same thing, but has some similarities. Next, we have two places where energy both exists and is usually lost, and that's going to be light and heat. So light and heat are both forms of energy. They are both very important forms of energy to our life. They are also the ways by which energy in a system can most easily be lost. So, for example, if we're looking at an electric circuit, most energy in an electric circuit is lost due to heat. So they're things that are both really fundamental to life on Earth, but also a method by which we can lose that energy. So one way that we can categorize energy is by essentially kinetic versus potential, or energy that's being used versus energy that is being stored. So our stored energy include nuclear potential, again, the nuclear potential, the chemical potential, the gravitational potential, the electrical energy, and our elastic potential energy. And then we can talk about our energy that is being used. Light, heat, kinetic energy. So we're seeing the effects of that, right? So for example, our electrical energy is used to light a light bulb. Our chemical energy is used to help us move or to help us heat our bodies. So these are some examples. So this is one really easy way to categorize energy. Now, in this class, there are 3 kinds of energy that we're going to be focusing on in this unit. So we are going to be learning a lot about the gravitational potential energy. You're going to learn a lot about elastic potential energy, and oh man, you're going to learn a lot about kinetic energy. The other energies in here, you're not going to see as much of. We're going to in this unit. We will, however, cover electrical energy in our electricity unit. We'll cover heat in our thermodynamics unit. And the chemical potential and nuclear potential we'll cover in our energy sources unit, which is a really fun one. However, for this unit, again, elastic potential, gravitational potential, and kinetic energy are going to be our focuses. So let's start with kinetic energy. So the equation for calculating kinetic energy is given by K, or our kinetic energy, is equal to 1/2 times our mass times our velocity squared. Now, I say velocity, really, it doesn't matter if we're talking about speed or velocity. because as you can see, the square here is going to cancel out any positive or negative sign that our velocity or our speed has. So our direction doesn't matter. And in fact, energy, regardless of whether it's kinetic or potential, energy is a scalar. So what's really nice about that is that you don't have to worry about the direction that something is moving in. You don't need to worry about the direction that something is above a surface. You need to worry about the direction that something is stretched in. The energy exists as just a raw number with a unit without any direction. So you guys finally get to move away from having to worry about direction. So anywho, let's go ahead and move forward to an example problem. So in this example problem, you are going to figure out the kinetic energy of an electron. So an electron has a mass of 9.1 times 10 to the negative 31st, and you can see I made a little mistake here and forgot to write in kilograms, but that's what our units are going to be in. And it travels at a speed of 2.2 times 10 to the 6th meters per second around a hydrogen nucleus. What is its kinetic energy? So let's go ahead and start by listing out our givens. So I know that the mass of my electron is 9.1 times 10 to the negative 31st kilograms. I also know that its speed is 2.2 times 10 to the 6th meters per second, and that my unknown is my kinetic energy K, since my question is asking me for my kinetic energy. So I know that the equation for kinetic energy is the equation that we just learned, and that is, of course, K equals 1/2 mv squared. And I can go ahead and now substitute and solve in my numbers since K is already by itself. So I know that K is equal to 1/2 times m, or 9.1 times 10 to the negative 21st, times v squared, so 2.2 times 10 to the 6th squared. Putting all of that information into my calculator, I get that K is equal to 2.2 times 10 to the negative 18th joules. And that J that I just wrote stands for, again, as you heard me say, that stands for joules, which is going to be the unit that we use for energy. So that is our standard international unit for energy. So the next kind of energy I'd like for us to talk about is the gravitational potential energy. This is the energy that something has because it's held above the ground, essentially. Now I get to decide where the ground is, right? So if I'm holding something and it's going to land on my table, then the table should be my base. Whereas if I'm holding something up and it's going to land on the ground, then the ground should be my base. If I'm 7 stories up in a building, the floor of the building, the floor that I'm standing on might be my base rather than the ground outside. So I think the point that I'm making here is that you have to decide what your 0 point is when you calculate gravitational potential energy. And usually it should be that when something hits whatever your ground is, it's going to be 0. But we worry about how high we are relative to that 0 versus how high we are relative to the center of the earth or the surface of the earth, whatever that is. So our 0 point is arbitrary, but it needs to be kept constant throughout a problem. Anyway, gravitational potential energy. We're gonna always represent our potential energy using a U, and that little g here suggests that it tells us that it's gravitational rather than elastic. Next, we know that we can see from this equation that our gravitational potential energy is equal to our mass times little g, so 9.8, times how high we are above the ground. So our height away from, again, whatever our 0 point is. Now, one thing I would like to point out is that mg is the same thing as the gravitational force, or if you want to call it, your weight. So if you're given weight instead of mass, you can just plug that in for mg and multiply that by height. So you don't have to multiply that by little g. So one thing to look out for, again, is do you have your mass measured in kilograms, or do you have your weight measured in newtons? Because those two things are going to slightly affect how you use this equation. So let's go ahead and look at an example of that. Al holds a 10 Newton apple 2 meters above Isaac's head. what is its potential energy relative to Isaac? So we know that Isaac's head is going to be our 0, and so we can just keep that 2 meters as our 2 meters. So again, that relative to Isaac is what we're finding is really useful here for telling us what our 0 is. Now, you may not always get your 0, but I trust that most people will be able to kind of tell from the problem what it should be. Do not overthink your 0. Make it whatever feels like the most obvious. Usually, again, the ground. In this case, Isaac's head. But whatever we're measuring from is going to be our 0. So let's go ahead and let's list out our givens. So I know that my weight is 10 newtons. I also know that my height is 2 meters. My apple is 2 meters above Isaac's head. And I know that my unknown is going to be my potential energy, and specifically my gravitational potential energy. And I know it's gravitational because we're worried about something being held up in the air, not about something being stretched. So I know the equation for gravitational potential energy is going to be given by UG is equal to mgh. However, I also know that weight is equal to mg. So, therefore, UG is equal to weight times my height. Or again, you can write FG instead of weight. And in fact, I'm actually going to go back and replace all of my W's with FG because we are in fact going to be using another thing in this unit that uses the letter W, and I don't want this to be terribly confusing. So let me go ahead and go back. Gravitational force, gravitational force, gravitational force. And again, we know this is our force of gravity, not our mass, because it's given in newtons, not kilograms. So here's our equation, and you'll notice that my equation has my unknown by itself and has substituted in my givens in a way that makes sense. So instead of having mg and having to find that in my substitute and solve stage, I have shown how I can go from mg to weight. So now I'm ready to sub and solve. So I know that my gravitational potential energy is equal to Fg times h, or therefore is equal to 10 times 2. And my gravitational potential energy here is 20 joules. That's a J, by the way. It's a little messy, I know. So there you go, guys. I have solved this problem. Let's go to the next one. So in this last equation that we're going to learn is our elastic potential energy. And again, our symbolism is pretty similar, right? We have U for potential energy. We have an E telling us that it is the elastic potential energy. And then we can see that our elastic potential energy is equal to 1/2 times K, which is our spring constant. So that's kind of how stretchy, again, our elastic is, times x squared, where x is how far it is stretched. So I'm going to have the stretch distance. And so you can see here that elastic potential energy refers to things like rubber bands. We can also use it for springs because, again, we're looking at stretching and compressing and how that affects our energy. So let's go ahead and look at an example. A spring has an elastic potential energy of 10 joules when it is stretched out 20 centimeters. What is the value of the spring constant K for this spring? And in this question, we're flipping things around a little bit, and instead of finding U sub E, our elastic potential energy, we're going to use our elastic potential energy to solve for K. So let's start by writing out our givens. And in this question, we know that UE is equal to 10 joules. And guys, just note, PE means potential energy. I tend to shorthand that a good bit. KE is what we'll use instead of kinetic energy. Again, as a shorthand, both are fine. I like to shorthand it because, why type a dozen letters when you can type 2? So our elastic potential energy is equal to 10 joules, and our x is 20 centimeters, or 20 times 10 to the negative 2 meters, or 0.2 meters. I'm going to leave with that last one because it's the nicest looking one. Our unknown is K. our spring constant. So our equation here is going to be our spring elastic potential energy equation. So UE is equal to 1/2 kx squared, or K is equal to 2 times UE over x squared. And I got that by multiplying both sides by 2 to get rid of that 1/2, and dividing both sides by x squared to get rid of the x squared and put K by itself. And I like to do this in my equation step because often I'll find that things will cancel and it makes life a lot easier. So let's go ahead and sub and solve. So I know that K is equal to 2UE over x squared, or K is equal to 2 times 10 over 0.2 squared. And when I stick all that in my calculator, what I'll find is that K is equal to 500 newtons per meter. And there you have it, folks. Here is a third energy example problem. And again, in this one, we were using energy to solve for something else, which is something that you will very much be asked to do in this unit. So let's go ahead and talk takeaways. First, of course, there are many different types of energy. One easy way to categorize energy is by calling it either kinetic or potential. So it's either stored or used. Or, well, actually, really, used or stored, right? Kinetic is used, potential is stored. We can calculate kinetic energy, gravitational potential energy, and elastic potential energy with those given equations. So guys, it is now your turn to try practicing with our 3 kinds of energy. Best of luck and happy solving!